Hi everybody, very good morning. Yeah, so we have very less people, but I think it's okay. Right, let me share my screen. Right, so we were doing coordination compounds, if you can remember. Right, so last class we have been doing the CFT. Right, hope you remember this. How the crystal field diagram splitting is going to happen. Right, they're going to be this. Strong field ligand pairing will happen, weak field ligand pairing will not happen, and we found out how to calculate the magnetic moments, paramagnetism, diamagnetism, everything we saw. That is only we saw only for octahedral complexes, isn't it? Right. So today we'll be doing tetrahedral complexes, right? Okay, and with that, this particular chapter will be over. Right? Anybody has any particular questions you want to ask me regarding the previous class?
No, sir.
Okay, good. Right. So after this chapter is over, we'll be starting with what is that? Chemical kinetics, as we decided. Okay. Right. So here, what happened? 1 second. Okay. Right. So today we'll see CFT for tetrahedral complexes. Okay. Right. So now again, how we started, if you can remember, how we started with your directions of ligand approach, right? So now what you have to understand is we have a tetrahedral complex like this, right? Say we have a metal, right? And we have something like this, isn't it? Right? This is say ligand, 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 ligand. This is a tetrahedral shape, is it not? Now we know what this wedge represents, what this dash represents, right? Wedge is representing that the bond is coming towards you, right? And the dash is representing that the bond is going away from you. That is behind the screen. This wedge represents that the bond is coming outside of the screen, right? Now, if you actually check properly, right? If you check properly, like what is the directions of ligand approach, right? For a tetrahedral complex, right? Do you remember what was the directions of ligand approach in case of an octahedral complex? Do you remember the directions of ligand approach for octahedral complex? What is the direction of ligand approach for octahedral complexes? Anybody remembers? In which direction, or say we know, right? Was basically we're talking in terms of coordinate axis, right? So what was the direction? Anybody remembers for octahedral complexes? Only if you understand that, we'll be able to understand how the degeneracy is lost, right? Yes, do you remember that? What was the direction of ligand approach for octahedral complexes? Why is it that here, look at this. Where are you? Yeah. Why is it that the dx squared minus y squared and dz squared is having higher energy than your dxy, yz, and zx? What was the reason here? Do you remember?
Sir, it approaches along the XYZ axis. The octahedral.
Okay. No. Come again.
It approaches along the XYZ axis.
Correct. The directions of ligand approach was along the XYZ axis. Is it not? Along x, along minus x, y minus y, z minus z. Is it not? And we know, obviously, whichever lobe is going to point along the axis for the d orbital, they will suffer more repulsion. right? And we know dx1 minus y squared and dz squared is having the lowest pointed along the axis, and even the directions of ligand approach in the same direction. That is why those two orbitals were having higher energy, because they are going to suffer lesser repulsion, right? Now, same way here we have to check what is the direction of ligand approach. Okay. Now, in tetrahedral complexes, maybe it will be a little difficult for me to show it in the 2D for you, but all that you can understand is that the directions of ligand approach, is in between the axis, right? In between axis. For example, say if I have X, Y, Z, this is say for example Z axis Z, this is say Y, this is your Z, right? The directions of ligand approach are going to be along in between your axis like this. Okay, not along the axis, right? In between your axis, we are going to have the directions of ligand approach. Again, this is a very, very important point. Okay, right. Now, can I expect the exactly opposite splitting as in the case of your octahedral complexes? Because there the directions of ligand approach was along the XYZ axis, right? But in case of a tetrahedral complexes, I told you that now it is going to be in between the axis. So whichever of the d orbitals which are having the lobes in between, which are pointed in between the axis, will suffer more repulsion now, is it not? Right? So again, we know the shapes. So can I tell that the dxy, dyz, and dxz will suffer more repulsion? Does anybody has any objection to this point? Is everybody okay with this? Right, obviously, right? So because these are the d orbitals which are having the lobes pointed in between xy axis, in between the y axis, in between x axis, and the directions of ligand approach is also in the same direction. So definitely they will suffer more repulsion. So they will be higher in energy in this case. Okay, they will be higher in energy in this case. Okay, and obviously the other two that is dx squared minus y squared and dz squared, which are having the lobe which are pointed along the axis, will have repulsion, but not as much repulsion as in these cases, right? So they will suffer lesser repulsion, right? Okay, now can we go for the splitting diagram? Very simple, right? Okay, so if I go for the splitting diagram, right? Say this was your energy axis along the y, right? Okay. Now we know that initially in the absence of the d orbit, absence of the ligands, all the d orbitals are having lesser energy and they were degenerated. No issues, right? Let me little extend it. Okay, right? So in the this is in the absence of ligands, right? In the absence of ligands, all the d orbitals are having lesser energy and they are degenerated. Okay. Now, when the ligands are approaching, right? When the ligands are approaching, all the d orbitals would have increased their energy, no doubt, and the degeneracy is still there, right? The ligand has not approached fully; it is still in the process, right? So here it's ligand approaching, right? So since the ligand is approaching, now can someone tell me why is it that the energy of the d orbitals are increasing? We saw an octahedral, right? Why is it that the energy of the d orbitals are increasing here when the ligand is approaching? Why? Why? In the absence of ligands, lesser energy, but if the ligand is approaching, now they're going to have increase in energy. Why? What was the reason? Nobody remembers. I'll give you 10 more seconds to think about it. Why is it that the ligand, the d orbital's energy is increasing when the ligand is approaching? Why? Think about it. Okay, again, it's all about repulsion, isn't it? right? We are going to have some electrons in the metal. These are metals, d orbital only, right? This is again metals, d orbital. Okay, right. So the metal's d orbital electron, or say the electrons in the metal, will have repulsion with what? With the ligand's electron, right? So why is the increased energy? Is because the repulsion between the electrons of metal and the electrons of ligand are going to have so much repulsion, and that's the reason why the d orbital's energy is increasing. Okay, right? That makes sense, right? Okay. Now the ligand has fully approached, right? The ligand is in its position, right? Now what is going to happen? Now the degeneracy will be lost. Okay, guys, I have been using this term degeneracy, degenerate, all these things. At least you remember what do you mean by degeneracy? What do you mean by degenerate orbitals? What is it? What are degenerate orbitals?
Same energy level.
Good. Right? Degenerate orbitals means orbitals which are having same energy. That's it. Right? Good. Okay. Now, when the ligand has completely approached, when they are in their own positions in the tetrahedral shape, right? Now the degeneracy is going to get lost, and we know which is going to have higher energy and which is going to have lesser energy. Is it not? We have already understood that your dxy, dyz, and dzx, and I know this set, right? This set is nothing but your T2G set, right? And this set is nothing but your EG set, right? This is your EG set, and this is your T2G set, right? Okay. So in this case, the splitting is going to happen like this, right? We are going to have 3 orbitals of higher energy, right? And that is nothing but your T2G, right? And we are going to have 2 orbitals of lesser energy, and this is your EG set. And we know what are the orbitals also. This is nothing but your dxy, dyz, dxz. And these are nothing but dx squared minus y squared and dz squared. Right? Okay. Now that's it. This is what happens in case of your octahedral complexes. Right? And again, this particular, this is your average energy, and this is also called as your barycenter. Right? Okay. And obviously the total energy difference between these two, the total energy difference between these two, that is the energy difference between EG and T2G, this is going to be called as del T. Now, last time we called it as del O because it was octahedral complexes, and this time we are going to call it as del T. Okay, right. And in this time, this is going to be plus 0.4 del T, and this energy difference between the barycenter and your EG is going to be minus 0.6 del T. Okay, this is minus plus 0.4 del T, and this is minus 0.6 del T. Exactly ulta, right? Whatever you saw in the case of octahedral, exactly make it ulta. Okay, right. Now, I'm going to tell you one thing, and you are going to give me a reason. Think about it. Okay, del T, if I compare the amount of splitting energy in case of tetrahedral complexes, right, and if I compare del O, that is splitting energy in octahedral complexes, right, which do you think will be higher, and what is the reason? Okay, what is the reason? We'll come back to that later. Everybody, go to your chat box, right? Go to your chat box and tell me which will be greater, octahedral or tetrahedral splitting energy. Go for it. It is just a guessing game. You need, it doesn't matter whether you're right or wrong. Just tell what you feel, right? Which is going to be higher, splitting energy in octahedral complexes or splitting energy in tetrahedral complexes? Which is going to be higher? What do you think? Go for it. Put it up, put the answer in the chat box. Come on, don't wait. Just put your answers. Okay, Ashik says it's octahedral. Go on, people. We have 9 students here. It doesn't matter whether you're right or wrong. Okay, Nikhilesh says octahedral. Okay. Then go on. Okay, Devesh says octahedral. Okay. Anandita says octahedral. Akshaya says also octahedral. Okay. Soma Junaidi. Nobody says tetrahedral. Okay, Fine. All of you are giving this answer. Anybody wants to pop in and tell me, sir, this is the reason. This is what at least I think is the reason. Octahedral is correct. Okay. Right. All of you are right. Octahedral splitting energy is indeed going to be greater than the tetrahedral splitting energy. No doubt about it. Right. But anybody wants to come up with a reason? Like say again, what do you think will be the reason? Yes, whatever you thought, like you gave some answer, right? You might have thought something right in your head, right? Okay, maybe this thing. Go on, people. Anyone wants to pop in and just give their reasons? Again, it need not see. We are not geniuses here, right? We are here to learn, right? I am just trying to make the learning process a little more interesting. That's all I'm trying to do, right? So whatever you have in your head, this is just our classroom. You have been seeing me for almost 2 years. I mean, some people have been seeing me from 11th class also. It really doesn't matter. Nobody is going to judge, right? So go on. Whatever you think, you can put it a heart. What do you think about it? Why is it that the octahedral splitting energy is going to be higher than the tetrahedral? Okay, I'll give you one clue. It is something to do with the electrostatic forces. Okay, fine. See, people, we told in case of crystal field theory, all the interactions, the assumptions, if you can remember, what are the assumptions we made in crystal field theory? One of the assumptions was all the interaction between the metal and ligand is going to be purely electrostatic, either attractive force or repulsive force. Yes? Okay, right. Now, when I talk about repulsion, we have been talking mostly about repulsion only here. Right. Now, in case of tetrahedral complexes, how many ligands are there? Yes, in case of tetrahedral complexes, how many ligands are there? How many ligands in tetrahedral complex?
4.
4. Good. Right. We have only 4 ligands. Okay. In octahedral complexes, how many ligands we have?
6, right?
6. Good. Right. Obviously, coordination number is 4 means, I mean, if at all I consider monodentate ligands, right? Monodentate ligands, you can see here are 4 because its coordination number is 4. And in case of octahedral complexes, 6 ligands were there. No doubt about it, right? So now think about repulsion. We are always talking only about repulsion. More the repulsion, more the splitting. Is it not? Now here I have only 4 ligands, and there in case of octahedral complexes, I had 6 ligands. Obviously, the amount of repulsion is going to be more in the case of octahedral complexes. And in case of tetrahedral complexes, we have only 4 ligands. Repulsion will be there, but not so much as in the case of octahedral complexes. It's all about higher repulsion, right? More ligands, more electrons, more repulsion. So a tetrahedral has only 4, octahedral has 6. So that is the reason why we have octahedral splitting energy to be higher than the tetrahedral splitting energy, right? I hope this makes sense, right? They actually will be able to give a proper number also, right? I don't know if this is there in your syllabus, but we will be able to give that. Del T is equal to 2 by 9 or 4 by 3. I forgot. Okay, I think it's 4 by 3 of...
Is it 4 by 9, right?
4 by 9, huh? Okay. Right? So 4 by 9 of del O. This is the relationship. Okay. Now you can see, obviously, this should be higher, this should be lesser. Right? Okay, this is the relationship. Now you can easily understand that del O is indeed going to be greater than tetrahedral complexes. Okay, right. Now, how we did in the case of octahedral complexes, the electronic configuration. Say, for example, if I have D1, right? For example, if I have D1, right? So now in this case, we know the lower energy is Eg, higher energy is T2G. It's exactly ulta. right? So when I go for D1 configuration, how can we write? The first is EG, then T2G here, right? Is it not? Okay, now here we have 2, here we have 3. So obviously we'll put the 1 electron here, EG1, T2G 0, right? When I go to D2, okay, when I go to D2 configuration, right? We have EG2, T2G0. We know how is it going to look, right? 1, 2, done. Great. Now, when I go to D3, right? Now again we'll have a problem, isn't it? Right? We can either have, let me write this little down. Right? So when we go for D3, we can either have EG3, EG3 T20. That means it is going to look like this. 2 electrons here, 1 electron here. Or we could have had EG2 T2G1. Right? That means here we could have had 2 electrons, and here we could have had 1 electron. Now, then we decided based on what was the ligand, right? Based on what was the ligand, right? So we said now we can have two cases. Case 1, that is del T less than pairing energy. Case 2, del T greater than pairing energy. Is it not? Right? The same happened with the octahedral complexes. Del O less than P or del T greater than P. I know what is P. P is pairing energy. The pairing energy is the energy to overcome the repulsion and then go for pairing. Is it not? Right. Now, people, one strange thing will happen in the case of tetrahedral complexes. Okay, one strange thing is going to happen in the case of tetrahedral complexes. What is going to happen is this is always true. Right? That means this does not exist. Your delta T, that is your splitting energy in tetrahedral complexes, can never, ever be greater than your pairing energy. Now, the reason is very obvious, right? Because compared to your octahedral complexes, tetrahedral splitting energy is very small, right? Tetrahedral splitting energy is very small. So since it's very small, it cannot be greater than the pairing energy, right? It cannot be greater than the pairing energy, right? Now, we know if the pairing energy is greater, pairing will not happen because pairing energy is very high. Pairing will not happen, right? Obviously, the electron will shift to the higher energy orbital. That is the case, whatever be the ligand, whether it's a strong field ligand or a weak field ligand, there is no case of pairing happening in case of tetrahedral complexes. Again and again, I'm repeating. There is no pairing happening in the case of tetrahedral complexes. That means this is absolutely wrong, right? This is what is going to be correct. Okay, this is the one that is going to be correct. Okay, right? Because we understood that the del O is greater. Obviously, then we can have two cases between pairing energy and stuff. But here del T is less, right? This cannot be the case at all, right? Pairing energy will always be greater than the del T. So this only is always correct, right? There is no case where you can have the other case coming up. Right, so D4 again you will go for the electron here, D5 again electron here, then D6 will go for pairing, like this you will do. Okay, right? That is how you should do in case of tetrahedral complexes. Right? Fine. So that's it. That is all about your. So again, if I ask you, if I have say Ni Cn 4 times, say 4 minus will not come. Say this is 2 minus. Right? If I ask you to find the magnetic moment, how do you find out? You have to understand that this is Ni is going to be in N. Guys, I'll be back in a minute. Just 1 minute. So yeah, so if I have to calculate the magnetic moment of this particular complex, right? So here we understand that x minus 4 equal to minus 2. So x is going to be here plus 2 configuration, right? Okay. So now I can easily say plus 2 means nickel actually would have had 4s2 3d8, right? 4s2 3d8. Now if it's Ni2 plus means all I would have had is 3d8 configuration. Right? So 3d8 is very simple. Let us see what is going to happen. So 3d8, how do we write in terms of T2G and Eg? So here it is tetrahedral. So first we'll write Eg, then we'll write T2G because Eg is smaller energy, right? So 1, 2, 1, 2, 3, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Fine. So we have only two one-paired electrons, n is 2. So we can write root of 2 into 2 plus 2, which is nothing but root of 2 into 4, right? So root of 6 Bohr magneton will be the answer to this question. Very simple. Okay, right. So you will 99% you will not be able to you will not be asked to find the magnetic moment of tetrahedral complexes, right? Because it is a little controversial, right? But octahedral complexes, yes, they'll definitely ask you, right? Okay. Now, another thing, what and all you'll be able to do with your CFT, obviously, you'll be able to talk about the strength of the ligands and stuff, how the bonding is happening and still stuff, right? You will be able to find other thing also, right? What you will be able to find is the color of the octahedral complexes. Color or not, octahedral complexes, color of the complexes. Okay, right. Now, do you have this in your syllabus? How do you establish whether a particular compound is colored or not? Okay, I think it should be there. Anyways, we'll see this. Right. Only the application part and the isomerism is deleted. Right. Okay. So people, first of all, what you have to understand is why is it that or how is it that you are able to see some colors? Right. Now, what we have to understand is, right, see, there should be some electron in some ground state. Right, there should be some electron in the ground state, and this is your this is your excited state. That is higher energy orbitals. Okay, that is your higher energy orbitals. Okay, now say some kind of radiation, some kind of energy is absorbed by this electron. Okay, some kind of energy is absorbed by this electron. Okay, so obviously it is going to go and shift here, right? If it shifts here, if it shifts here, here it cannot stay for a long amount of time, right? Here it cannot stay for longer amount of time because the excited state is unstable. Okay, so what will happen is that it is actually going to come to some other level. It's going to be in between. It is going to come like this. Okay, again, I repeat what is happening here. We have one electron in the ground state. Okay, now that is going to absorb some energy. Okay, and it is going to go to the excited state. Okay, and it is going to go to the excited state. And as I told you, it will not be able to stay in the excited state for a long amount of time. Right. So what is going to do? It is going to come back. It is not going to come back to the ground state not directly, but actually it is going to come back to some intermediate level. Right. This is how it is going to be present. And whenever electron comes from a higher energy level to a lower energy level, there will always be some energy released. Right. There will always be some energy released. Okay, now this is the entire process, or this is the overall thing which you have to understand for how is it that you're able to see some colors, right? Now, if this energy absorbed, right, this energy absorbed, right, is in the visible region, right, is in the visible region. Okay, say for example, this particular electron has this thing, say absorbed red color. Right, it does. Again, all the colors are also electromagnetic radiations, right? Hope you understand that. Visible region will have all the colors, right? All those are electromagnetic radiations, right? Say this one has absorbed red color. Okay, now if this absorbs red color, you will not see red color of this particular thing. Say this is some species. Okay, this is some chemical species, and it is absorbing some red color. Okay, right. Now the energy released will always be complementary. Now, if you think about it, the energy absorbed right, and the energy released, right, we will say that they are complementary to each other, right? They are complementary to each other. Okay, that means for every color which is getting absorbed, there will be a complementary color. For example, if red is absorbed, I think the complementary color will be yellow, right? So if something is able to absorb red color, it will look yellow in color. Again, I repeat, if I am absorbing red color, how I look in appearance will be yellow in color. So for example, if it is going to absorb, say, I don't remember the exact complementary colors, right? But I think we can check that. We'll go to Google and check this. Okay, so this is what you have to understand. I think I told something wrong, right? So you understand, right? Say if red is absorbed, let me actually, okay, you can understand, right? If red is absorbed, the color will be green, right? If yellow is absorbed, then it will be purple, right? If blue is absorbed, the color will be orange, right? So like that, these are all the complementary colors. You can even go, like I just typed complementary colors and I'm just showing you in the Google images, right? You can also learn it, right? If you can remember what are the complementary colors, it's very good. But for an exam point of view, you do not remember anything. Okay, right? Okay, so all that you have to understand is whatever is absorbed, right? Whatever is absorbed, that complementary color will be the color of the complex. That is all you have to understand. If, say, for example, yellow color is absorbed, the complex will look purple in color. If red color is absorbed, the complex will look green in color. Like that, that is how the complementary color works. Okay, right. So that is what I wanted to tell you. Now, okay, fine. We understood that this is the process of something to be colored. Okay, right. But not all the complexes will be colored, right? Some of the complexes will not be colored also, right? Now, how do you understand whether by even you don't know anything about the complex, say you know what are the metal, what are the ligands, what is the oxidation state, that much only you know, right? You will not be able to predict which color it will be. That yeah, sorry. You will not be able to predict which color it will be, but you will be able to predict whether it is going to be colored or not. First of all, we will be able to predict whether the compound will be colored or not, but we will not be able to predict which color it will be. That is very difficult. Okay, but we will be able to predict whether the particular complex will be colored or not colored. That will be able to predict. Okay, right. Now, people, if you look into this carefully, right, we need some electron, right? We need the first condition, right? The first condition is that we need at least one unpaired electron. At least one unpaired electron should be there. Only then it will be able to go to the higher energy level. Makes sense, right? You can ask me, sir, what if I have paired electron? Paired electron, you will not be able first. See, the thing is, if at all I have a paired electron, first you have to dissociate them. Right? First you have to dissociate them, then only it can undergo the transition, that is lower energy to higher energy. Okay, but if I have an unpaired electron, it's very easy. Okay, so one very important condition is that we need to have unpaired electrons present. Okay, we need to have unpaired electron present for us to for the compound to have any color. Right. Second thing is that the higher energy orbitals, right, should be present. Right, should be vacant, I should say, should be vacant. Is it not? Because the electron absorbed, unpaired electron is there, but there is no place for the electron to go. Then what will happen? Nothing will happen. Isn't it? So energy should be absorbed by the unpaired electron and it has to go to the higher energy level. So the higher energy level should be what? It should be vacant. Only then it will be able to go occupy that. All right. Okay. Again, makes sense. Right. Now, even if you don't understand any of this, right? Now it's very, 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 very simple to understand whether a compound is going to be colored or not in general, right? If you have a D0 configuration, that is, there are no electrons in D, or if you have a D10 configuration, right, you can easily say the compound will not be colored. Very important point, right? Because first of all, it doesn't have an electron in D, right? And here I have no unpaired electron. So in both these cases, you will understand that the compound cannot be colored, right? But any other configuration, say from D1 to D9, right? It's okay. The compound will be colored, right? The compound will be colored. Okay, this is what we understand from the overall analysis. Okay, D0 and D10 configurations will not be colored, but again, what we saw as the reasons are only one of the reasons. Okay, if you go to little higher levels of chemistry, you will understand that with very rare cases, D0 and D10 can also be colored, but the reasons are very different. We have something called as LMCT, we have MLCT, that is ligand to metal charge transfer, metal to ligand charge transfer. These are all higher levels. If you are interested, you can even study about it. It's not that difficult to understand also. Maybe if once we complete the syllabus, maybe we'll talk about these things. Okay, but for now, if you have D0 or a D10 configuration, you can blindly say that we were talking about the metal. Okay, if the metal has D0 or D10, it will not be colored. D1 to D9, it is okay. It is definitely going to be colored. Okay, right? I hope that made sense, right? So that is how you will be able to talk about the color of the complex also, right? And at last, what are we going to do now? No, I think we have metal and metal carbonate also. Okay, no issues. Now what we're going to see is the limitations. Limitations of CFP, right? Okay, even though it is able to explain a lot of things, obviously it will have its own limitations. Okay, right? What are the limitations? We try to understand. First one, right? What is that? What CFP said is that all the interaction between the metal and the ligand are purely electrostatic, right? All the interaction between the metal and the ligand are purely electrostatic. Means, for example, if you have a M plus and say a negative charge X minus, they should have a stronger attractive force. Right? They should have a stronger attractive force when I have a M plus with the ligand having a lone pair of electrons. Basically, this is a negatively charged ligand. This is a neutral ligand. Right? So the interaction between the negatively charged ligand and the metal should be stronger than in the case of a ligand which is neutral with the metal, which is going to have a positive charge. That interaction, that attractive force must be little weaker. That is what we expect, isn't it? Because CFT said that it is going to be purely electrostatic, either attractive force or repulsive force. Is it not? But what we see that, for example, CO, right? CO is actually having what? Is actually having is a strong field ligand. That means that will have a stronger interaction. Say, for example, Cl minus, which is a negatively charged ligand, should have had a stronger interaction with your metal. Right? But what is actually having stronger interaction? CO. This is a strong field ligand, this is a weak field ligand. Is it not? So again, the strength of the ligand is not explained. Right? Like owing to the assumptions that are made in your CFT, saying that all the attraction, all the interactions are going to be only attractive forces or repulsive forces, given that the CO should be a weak field ligand and Cl minus should have been strong field ligand. But what we see in reality is absolutely opposite. Right? I hope that makes sense. Right? And then he said that, the CFT said that all the ligands are going to be point charges, right? So the shapes, right, are not that much explained, right? Because he said that all the, I would not say shapes, but say the volumes of the complexes, right? They will have some volume, right? But he said that all the metal and the ligand are to be considered as your point charges, right? So point charge is literally no volume, isn't it? Point charge is literally no volume. Again, volumes will become a problem if I'm going to say, if at all I want to do some volume calculations, right? Then it is actually going to become difficult with respect to CFT. right? Because it considered all the things to be point charges. Point charge means there is no volume at all, right? So these are all the different some of the limitations of CFT, even though it explains a lot of things, right? But still, some of the things are not explained properly. Okay, so with this, your CFT is done, right? Anybody has any questions to ask me? Any questions? Okay, fine. I hope everybody is following. Right now, the last part of the chapter is going to talk about organometallic chemistry or organometallic compounds. Okay, this is my favorite topic. Basically, this is an entire branch of chemistry. Okay, even though it comes under coordination complexes. Okay, but this organometallic chemistry itself, there's a separate chemistry like physical chemistry, organic chemistry, like that. We have something called as organometallic chemistry itself. That's a very huge area, right? But here we're going to discuss the introduction, right? Okay, so fine, people. So first you have to understand what you mean by organometallic complexes, right? Now, in simple words, if I have to put, there should be compounds. These are compounds which are having a carbon metal bond. Okay, right? Any compound which is having a carbon metal bond, those kind of complexes or those kind of compounds are what are called as organometallic complexes. Right now, think about it and tell me, you already know one organometallic compound. What is that? You already know one from organic chemistry. What is that?
Grignard reagent.
Absolutely right. Grignard reagent. What is there? Grignard reagent is having this CMG bond. Is it not? Right? We have RMGX basically, right? So we already have this CMG bond. So again, that's a beautiful example of an organometallic compound, right? So anything which has carbon metal bond is an example for your organometallic complexes. Okay, right. Now this organometallic complexes can be divided into three types. Okay, can be divided into three types. One, they can be sigma type, right? Or they can be pi type, or they can be sigma and pi type. Both sigma and pi. Okay, right? Sigma type, pi type, or sigma and pi. Both types can be there. Right. Now, what is sigma type? What is pi type? What is sigma and pi type? It's a type of bonding, right? If you have only sigma bond between your carbon and the metal, right? For example, Grignard reagent is going to have only CMG bond, right? So basically they will have only sigma bond. What bond are we talking about? We're talking about the carbon metal bond, right? If the carbon metal bond is having only sigma bond between them, those kind of organometallic complexes are going to be called as sigma type organometallic complexes or compounds. We cannot say complexes, right? They call it as sigma type organometallic compounds. Okay, right? So Grignard reagent is a very good example. RMGX is a very good example because you understand between carbon and Mg, they'll have only sigma bond, right? Okay. Now pi type, obviously they will have only pi type, only pi bonds between them, right? Okay. Now, we actually have a controversy here, right? Whenever we go for a pi bond will always be formed only after a formation of sigma bond. Is it not? For example, when I say a CC double bond is there, one bond is sigma, the first bond is always sigma bond, then only we go for a pi bond formation, right? But this kind of things are saying that only pi bonds are there. Weird, right? Because generally only we form pi bonds after the formation of sigma bond, right? But this kind of compounds, this kind of organometallic compounds are having what? Are having only pi bonds between the carbon and the metal. Again, it's not about anything else. Again, what bonds are we talking about? We are talking about the carbon metal bond. Okay, right. Now, how do we understand this? We will take an example, right? Example is ferrocene. Right, example is your ferrocene. Okay, ferrocene is going to look like this. Okay, right. Now we have one benzene ring, right, and we have another benzene ring. Okay, and we have the Fe2+ ion. Right. Now we understand that this round means what? There are basically 6 electrons, right? If they can just show it to you. Right. Now this 6 electrons, all the electrons are what? This is a pi bond, this is a pi bond, this is a pi bond, and there'll be 2 electrons, and all of them are in conjugation. That is why we don't represent it like this. We will be representing with the help of a circle. Is it not? That makes sense. Oh God, what is wrong? Okay, at last. Okay, so that is why what we say is that we will be representing with the help of a circle like this. Right. Now, what does the circle represent? The circle represents there are 6 electrons here. Again, this circle represents there are going to be 6 electrons here. Now, this 6 electrons and this 6 electrons are going to make a bond with this Fe2 plus. Right. So all the 6 electrons in conjugation, right, are going to be donated to your Fe2 plus. Same way, all the 6 electrons here are going to be donated to your Fe2 plus. Okay. Now, can we not easily understand that it is actually the pi electrons from the ligand? These are the ligands here. The benzene is the ligand, benzene is the ligand here, right? It is actually the pi electrons which are getting donated, not the sigma electrons. It's not a sigma bond. Why we call it as a pi bond? This is a pi bond, we say. Why is it a pi bond? Because it is the pi electrons which are actually forming your bond with your Fe2 plus, right? Now, there is another example. Maybe I can give you. Say, if you have an allyl compound, say this is a compound like this, right? And say we have a metal, right? Now, this is a pi electron, right? This is a pi bond. Now, that can be donated to the metal. Again, this is an example for a pi bond, right? So, whenever the electrons are getting donated from the pi electrons to the metal, those kind of compounds, those kind of organometallic compounds are what are going to be called as pi type organometallic compounds. Okay, so ferrosinus was one example. This is another example. You can have again the same thing can happen with the help of your Cr3 plus. That is also there. Check your textbooks. They would have maybe given some good examples. Okay. Again, these are what are any questions anybody has? Everybody understood? What do you mean by a pi type organometallic compound? Everybody understood? Any doubts anybody has? Okay, fine. I'm assuming that everybody is following, everybody is understanding. Good, right? So that is about your pi type. Sigma type, normal, nut reagent, all the other things, and pi type should have the pi electrons involved in your coordinate bond formation between the metal and the ligand. Very simple. Okay, fine. Now coming to the last type. Right, last type, which I'm going to say that we are going to have both sigma as well as pi type of bonding. Both are to be present. Okay. Now the example we can have is metal carbonyls. Right. Okay. Right. Example for this is metal carbonyls. Oh God. Sometimes it creates a lot of issues. Okay, right. Right. So the example for sigma and pi type are metal carbonyls. Okay. Now, what are metal carbonyls is very simple, right? So we need to have CO, that is carbon monoxide, as the ligand, right? And that is going to be bonded with your metal, right? So generally we will have this kind of coordination. Okay, right. Now you can ask me, sir, what are you saying? You said that it is going to have both sigma and pi bond, but here you're showing only sigma bond. This is your sigma bond, right? Where is the pi bond coming? We'll see that. How is it happening? Okay, right. Now this CO is a very special thing. Okay, this CO is a very special type. This not only CO, even we can have Cn minus as a ligand. The same thing will happen in the case of that also, right? But we will just see metal carbonates. Okay, right. So we understand that how a sigma bond is easily getting formed, right? Say sigma for sigma bond, right? How the donation is happening? The donation is coming from the filled orbital of carbon, right? The donation is happening like this, right? That filled orbital of carbon is donating electron to the empty orbital of your metal. This is not empty d orbital of the metal. Empty, you can write empty d orbital of the metal. Is it not? Now I can easily show this also, right? Say we have the metal which is having an empty orbital, and we have carbon monoxide which is having your electron present. Okay, now those two are going to come together. Normally, we know how sigma bond formation happens: head-on collision, right? The orbitals will come. Head-on collision is going to happen for a sigma bond, right? So we will have carbon. Say this is for carbon with O, and here we are going to have the 2 electron share. This is your normal sigma bond, right? Okay. Now, other than that, sometimes what can happen is this carbon, if you check, right, this carbon, the carbon monoxide, this carbon, if you check, this carbon is actually sp hybridized, right? See, the exact way to explain this should be in terms of molecular orbital theory, right? But that level of MOT we don't know yet. Okay, the exact way, the correct way to explain what exactly is happening here should be in terms of molecular orbital theory only, right? But that level of molecular orbital theory we don't know yet. Okay, that's why I'm talking in terms of hybridization, because you know hybridization. Okay, right. So we have this carbon to be sp hybridized. Now we can easily understand that this is going to have some empty orbitals also. That there will be some empty p orbitals here, right? They will have some empty p orbitals present, right? Okay, so now if they have empty p orbitals, they can accept electrons, right? They can accept electrons also, right? Obviously, it has some lone pair and all that can be donated, right? But it is going to have two empty p orbitals will be there, so definitely it can accept more number of electrons also. Okay, now how it can accept, let us try to understand. So if metal is having a d orbital, right? If metal is having a d orbital, and it is say it is having electron like this. Okay, this is your metals is d orbital, right? And it is having 2 extra electrons and already in the d orbital present. Okay, and you have the carbon of carbon monoxide to have an empty orbital like this, right? Now what can happen? They can laterally overlap. Lateral, this is head-on collision, this is lateral overlap, right? Now that we will be able to form, wait. Okay, something, oh God, this is very bad drawing. Okay, forget about it. I'll draw it here. So we have this one, and we are going to have the C of pen. Right? Okay. There are other things also present. Don't worry about it. Okay, and we have this also. Okay, and we have the oxygen also. Okay, now what you understand is that there can be electrons shared here. Now what is happening? The 2 electrons from metal is actually going into the empty d orbital, empty p orbital of carbon, right? Now can't you understand that this is actually a pi bond, right? This is actually a pi bond, is it not? So this is nothing but a pi bond, and obviously it can be formed only after a sigma bond formation. Right? That means I should have already had this one happen. right? I should have had 2 electrons here. This is your sigma bond. Right? This is a sigma bond. Okay, that has already happened. That is, this sigma bond is coming from carbon to metal. Look at the arrow mark, right? Carbon to metal. That's your coordinate bond. Now, how the pi bond is coming? Pi bond is coming like this, metal, right? The electrons are coming from metal, and it is going donated to get donated to the empty orbital of carbon. That is a pi bond. Okay. Now don't you see that we have sigma bond also as well as pi bond happening? Is it not? Right. Now this pi bond can also be called as a back bond. Right. This pi bond can also be called as a back bond. Okay, right. And whenever this back bond happens, right, whenever this pi bond formation is possible, now you understand that carbon monoxide is going to be C double bond O, right? Carbon monoxide is going to be C double bond O, very strong bond between carbon and oxygen, because we are going to have a triple bond, right? But when we have, say, this one, right, a coordinate bond is formed between this carbon and the metal, normal sigma bond, the CO bond strength weakens. The CO bond weakens. Right. Now, if I'm going to have a double bond between carbon, if I'm going to have one bond coming like this, another bond coming like this between carbon, now obviously carbon cannot have more than 4 bonds, so it is going to be a double bond. So CO bond is the weakest here. Obviously, we know double bond is stronger, triple bond is the strongest, then double bond comes, then single bond is the weakest. Right. Now, since we understand that we are going to have this pi bond also happening, that the double bond coming between the metal and the carbon, right? That is going to make sure that the carbon oxygen bond weakens. Why? Because we are going to have only double bond between carbon and oxygen. This is also a very important point. They'll ask you in the question, why is it that free carbon monoxide carbon oxygen bond is very strong, whereas when the metal carbonyl, the CO bond weakens? You have to tell that because of the bond formation, the CO bond weakens, and you have to tell that because of the pi bond formation, the carbon oxygen bond becomes a double bond, and that's the reason why it is going to become weakened. Okay, that's the reason why it is going to become weakened. That is what we need to answer these. That is how we need to answer these kind of questions, right? And done. We are done with coordination compounds. The end. Okay. Anybody has any questions to ask me? Any questions at all? Okay, in your book, these kind of diagrams, whatever I'm drawing, will be very easily, nicely given with the help of color codes and all. Please look into it. Now that you understand what exactly is happening, pi bond, sigma bond, once you look into the book, you'll be able to easily understand. Okay, right? So that is about our coordination compounds chapter. Good chapter, right? It was very interesting. At least it was interesting for me. I don't know how you felt it, right? Okay, so now what we'll do is maybe we will go for kinetics, right? We'll start with kinetics, right? Fine. Okay, let me, do you want this, this thing? Do you want this, what is that, notes, guys? Coordination compounds notes?
Yes, sir. Yes, sir.
Okay, can someone send me a hi? I'll just send it to you and you can send it across in WhatsApp. Hey, not here, man. In WhatsApp. Okay, Ananya. I'll send you. Please send it across. Okay. Let this get ready. It will take 2 minutes. Okay. Oh, I got so many highs. I don't know who. This is Ananya, I guess. 99620. This is Ananya. I don't know who's this. So many highs.
66229 is mine, sir.
66. Satyapriya. Okay, I don't know. I'll send it to some number. Okay. Please take care. Whose number is this? Okay, sent. So is anybody who is anybody is not getting from the particular person, then you can message me, okay, and I will send it across again for you. Okay, fine. So fine. So that's about coordination compounds. Next we will start with kinetics. Okay. Right. So the chapter's name is chemical kinetics, right? Okay. So what are we going to study in this chapter, right? Now, till now, right? In your 11th, or say in all the chapters of 11th, or in your chapters of 12th also, right? So whenever you saw a chemical reaction, right? We actually did not speak about whether the reaction will happen fast, very fast reaction, very slow reaction, or say we have to have a catalyst to increase the rate of the reaction. All those things we have been speaking. Like we didn't speak at all, right? Only in terms of catalyst, we know, okay, catalyst is the one which is going to increase or decrease the rate of the reaction. That we had understood. That we have been studying for the lower classes, right? Okay, in this chapter, we are actually going to study about the rate of a chemical reaction, how fast or how slow a chemical reaction happens. And we are going to delve into the mathematics of this. Okay, like say certain reactions are, we are not going to see why certain reactions are fast, why certain reactions are slow. That we are not going to see. That is not the thing here, right? But we are now trying to calculate, right, what will be the rate of a chemical reaction, right? Now in kinetics, in your physics, what you have done, you would have done about motion, right? What is kinetics? Basically, kinetics is nothing but you have the study of motion, isn't it? So there also you have studied about rates, right? Now different rates you have studied, right? The one rate you have studied is about velocity, right? The other rate you have studied about the acceleration, right? How do we define velocity? Velocity is, how do you define this? Velocity is velocity is, how do we define velocity? Really? How do
dx by
we?
dt.
That is the formula. How do you define velocity?
So maybe the speed at which something moves in a particular direction.
Okay, the exact definition what I was expecting is it is rate of change of dash. What? Rate of change
Displacement.
of, good, right? It is rate of change of displacement. Right? Now, look at this. Whenever we say rate of rate, I mean, in this case, is rate of change of displacement. Acceleration, you would have been defining it as rate of change of what? Acceleration, rate of change of
velocity.
right? Acceleration is rate of change of velocity. Okay, and we have something called as jerk. Jerk is rate of change of acceleration, like that. So whenever we speak about rate, right? Rate, whenever we speak about rate at which something is changing, right? Whenever we mention this term rate, we are talking with respect to time, right? As time progresses, right? As time passes, how that particular quantity is changing is what we are going to see is what we're going to study when we talk about rate, right? So when I say rate of change of displacement, what is the change in displacement? Del T. What is the change in displacement in a particular time period? That is what is your velocity. And as you said, it can be dx by dt. Right? It can be either dx by dt or del t divided by del t. That is basically nothing but change in displacement by change in time. So whenever we say about a rate, it is change in some quantity, change in something, right? Divided by change in time, right? Change in time. That is what we always tell when we talk about rate. Rate at which something is changing means what? As time progresses, how that particular quantity changes is what is called as rate. Okay, so here when we go to chemical kinetics, as I told, we are going to study about rate of chemical reaction. Then how can I say, sir, then is it actually going to be a change in chemical reaction by change in time? Doesn't make sense, right? Okay, we say, when I say rate of chemical reaction, we can say that our rate is equal to change. When I say rate of change of displacement, we took rate of change in displacement by change in time, right? So here, what if I say change in chemical reaction? That doesn't make sense at all. Change in chemical reaction by change in time does not make sense at all. This does not make sense, right? Because what do you mean by change in chemical reaction? Does not make sense. But if you see during a chemical reaction, what changes, right? If a chemical reaction happens, right, what changes? That if I can understand, then I will be able to speak about the rate of a reaction. Can you tell me during a chemical reaction, what is changing? Or no, don't tell me that reactants are getting reactants changing the product. That is obvious. What quantity is changing? Say if I have to talk about some quantity, some number, what is that number which is changing in case of a chemical reaction? Nothing changes?
Moles of reactant.
Good. Yes, number of moles of reactant keeps on changing. Number of moles of
Product
product
also.
keeps on changing. Yes, absolutely. Is it not? So, but instead of talking in terms of number of moles, we are going to talk in terms of concentration. Okay, so when I say rate of chemical reaction, what are we talking is rate of change of concentration. Because we understand that during a chemical reaction, the concentration of reactant keeps on changing, concentration of product also keeps on changing, right? And to be more specific, the concentration of reactant that why is it happening? Something is wrong. Let me drink some water. Just give me a moment, people. I have to go bring the water. I'll be back in 10 seconds. Okay, all right. So yeah, So we understood that when I say rate of a chemical reaction, in chemical reaction, what is changing? The concentrations of reactant and concentrations of products are changing. Okay, right. Now, how is it changing? We understand that during a chemical reaction, right? During a chemical reaction, the reactants giving products, right? Say if I start with say some 1m concentration and this is 0, this is at time t is equal to 0. Okay, at the starting of the reaction, right? Now, at say t is equal to 1 minute, right? At t is equal to 1 minute, what would have happened? Some of the reactant would have reacted and would have gone to the product side. Say out of this only 0.9 is remaining, and say here I got 0.1 m. Right? Say like this, like this, like this. Say at t is equal to 5 minutes. Say 0.5 is remaining here. 0.5 has come here. Right? So don't worry about the end of the reaction. It is not going to become 0. Okay. Remember that it will never become 0. Right? That never happens in a chemical reaction. The reasons are very various. Like that cannot happen simply like that. Okay. Anyways, so what are you seeing here is that as time progresses, right? As time progresses, the concentration of reactant, right? The concentration of reactant decreases because more and more reactants are consumed, is it not? And obviously, as the time progresses, the concentration of product keeps on increasing because you see 1.1, 0.5, here it is 1.9, 0.5, like that, it keeps on happening. Right? So during the course of a chemical reaction, more and more amount of reactant gets consumed. So the concentration of reactant decreases and more amount of product gets formed. So through the time process, you'll understand that the concentration of products keeps on increasing. Right? So that is that so you understand, right? As the time progresses, there is some change in concentration of the reactant and the product, but the reactant concentration is decreasing and the product concentration is increasing. Right? Okay. Now this we understood. So when I say rate of change of concentration, right? Now how do you mathematically write this? Right? Now when I said rate of change of displacement, we wrote change in displacement by change in time. Right? Here, when we say rate of change of concentration, then that rate is nothing but change in concentration. Whether it's reactant or product, that we'll see later. Right? Change in concentration divided by change in time. Right? This is the quantity which we are referring to. When I say rate in chemistry, rate of a chemical reaction in chemistry, we are always going to say change in concentration. Again, can be reactant, can be product, that we'll see later. Right? Generally, change in concentration by change in time. That is what we always speak. Right? So we can also write in the formula, we can write del C divided by del T. Okay, del C divided by del T. That way also we'll be able to write. Right? What is del C? Del C is change in concentration. Del T is change in time period. Okay. Now I can also write it like this sometimes. R is equal to dC divided by dt. That is also right. Okay. Now what is the difference between these two? When I write del, this is average rate. Right? And when I write D, this is your instantaneous rate. Instantaneous rate. Right? Now, what is the difference between these two? We'll understand. Both are change in concentration by change in time. Right? So for us to understand this, let us take a graph. Right? Let us see the graph for concentration versus time. Right? For a chemical reaction, say R giving P. Okay, it's a chemical reaction, and we are going to plot as the time progresses how the concentration of reactant and the concentration of product keeps on changing. What is the flow is what we are going to see. Right? Okay. Now, when I talk about reactant, for example, right? Say reactant initially would have had some concentration at time t is equal to 0. We understood, right? At time t is equal to 0, we had some amount of reactant, no amount of product. Yes. Okay. Right. So at time t is equal to 0, we have some amount of reactant, and as the time progresses, as the time increases, the concentration should decrease. Right. As the time increases, the concentration should decrease for a reactant. So you will see a graph something like this. Now you will see that the concentration will never become 0. If it touches here only, it is 0, right? It will never touch 0. Anyways, right. This is for the reactant. Okay. I mean some other color for product. Now say initially at time t is equal to 0, there was no product. So the concentration of product was 0. Right. Now as the time progresses, we see that the concentration of product keeps on increasing, right? The concentration of product keeps on increasing. This is for product. Okay, right. Now this we understood. Say for us to understand this, if I give you distance time graph, right? If I give you distance time graph and I say that this is the curve, how will you find the velocity from this? Right? If I give you distance time graph or say displacement time graph, whatever it is, how will you find the velocity from the graph? What will you do? What will you do? What is velocity? Change in time, change in change in displacement divided by change in time. So what we'll do, we will take two different distance values, right? And you will take that corresponding time periods, right? Now this thing is what is your del D, right? And this particular distance is what is your del T, right? So what is this thing? Del D by del T. So if I take this one, that is, say this is some D2, this is some D1, and this is say T1, and this is say T2. What do you write? We write V is equal to D2 minus D1 divided by T2 minus T1. What is this? What is from the graph I'm taking? What am I doing here? What am I doing here? Am I not taking slope? What is slope? How do you find slope? M. What is the formula? Y2 minus Y1 divided by X2 minus X1. The same thing only I did. Say I took D2, D1, T1, T2, X-axis, Y-axis. This is nothing but the slope. So from the distance time graph, if I ask you to calculate what is the velocity, all that we have to take is the slope. That is what we need to do. Right? The same thing can be done here also. Right? What is rate? Rate is del C divided by del T. Right? Del C divided by del T. So all that we have to take is the slope of this particular two curves. But again, you will get two different values. Right? You will get two different values. One for the reactant, one for the product. It is not that the rate of change of concentration of reactant will be equal to rate of change of concentration of product. That need not be the case. Might be same, might not be same. That depends on the chemical reaction. Okay, right. But we will get two different answers for sure, or at least two rates we will get. One is for the rate with respect to the reactant. The other one is for the rate with respect to the product. Right. Say if I have to calculate this, I can take say this particular slope. Right. This particular slope I can take. Say this is some C1, this is some C2, and say this is the corresponding time period. I will be able to calculate this. Okay, right. Say for a product I need to find, say I can take this one again, some time period, some two different concentrations, you'll be able to find the slope again. Right. So if at all the concentration time graph is given to you and you need to find what is the rate of the reaction or the rate with respect to the reactant or product, all that we need to take is the slope of the line. Right. Now, what am I trying to say? We saw that the rate can be, where is it? Yeah, the rate can be of two types. One, it can be average rate or it can be instantaneous rate. Okay. Now, what is the difference between these two is this del T is a finite value. Right. Say from 10 seconds to 15 seconds, we'll be able to do that. Right. But this dt, when I say, what am I trying to say? Where is the graph? Right. So this dt, if I say I am going to take a very small change in the time period, very, very, very small change in the time period. And for that small change, you will find a very, very small change in the concentration, say from 1 second to 1.0001 seconds. That is the time frame I'm taking, right? From 1 second to 1.0001 seconds. In that, there'll be a very small change in concentration. Right now, that particular in the small time period, small change in concentration, that particular thing is what is called as our instantaneous rate. Okay, that is what is called as our instantaneous rate. So what I can tell is this I'll be able to write. Right. Say when we write rate, right? We'll write it as del C divided by del T, right? Now, when I apply the limits where del T approaches 0, almost the change in time period is 0, from 1 to 1.0001, that becomes dc divided by dt. Okay, that becomes your dc divided by dt for the small change in time period. The small change in concentration, what is happening? That is your instantaneous rate. Okay, fine. I think we'll stop this for today. Okay, we'll stop this for today. We'll take up from here in the next class. Okay, any particular questions anybody has? Okay, fine. Thank you so much, people. We'll meet again in the class.